We want to begin a discussion on rotations, and we're going to find very many similarities between rotations and translations. Keep in mind a translation is movement in 2 or 3 dimensions. A rotation is going to be some sort of a motion around a center point, but that center point might be moving as well, so you're going to have combinations of rotations and translations. We're going to start off just by looking at rotations though. So if we're going to begin rotations, let's take a look at some of the variables, and if you notice, all of these variables you've seen before, it's just we put the word angular or rotational in front of them, and we're going to have some different names here, but the whole idea is that pretty much everything we've discussed up to this point has a rotational counterpart. So angular position or rotational position is very similar to linear position. If I set up an x and y axes, but I have maybe some shape rotating about some axis, then on that shape there is a point, and from the axis of rotation to that point with respect to, I'm going to call it the x-axis, but it doesn't really need to be, but generally we talk about the positive x-axis. That point is going to have some position measured as an angle from the positive x-axis. And so here's my positive x-axis again. Axis of rotation is here. This point out here has a position, and I'm going to measure that position with respect to the positive x-axis with some angle, and I'll use the Greek letter theta. Right, so angular position is measured with the Greek letter theta. Now, angle has no dimension, no mass, length, time, charge. We can measure theta in radians, or we can measure theta in degrees. And so there are units involved when I talk about angular position, but there are no dimensions there. Now keep in mind there are many different functions which cannot have dimensioned quantities, and trig functions are one of those. So when I talk about the sine of theta, theta does not have any dimension. It can be measured in radians or degrees, but it has no dimension. Exponentials are the same way, so I can have e to the theta, and that's fine. Logarithms as well, log of theta, that's fine. Those don't have any dimension to them, even if they're in radians or degrees. So when I talk about exponentials or logarithms, we almost always will be in radians. Now angular velocity will be defined pretty much the same way as linear velocity. So if you recall, linear velocity, by definition, was the derivative of position with respect to time. And in fact, when we talked about vector quantities, the vector velocity was the derivative of the vector position with respect to time. That's by definition. And so the same thing is going to hold true for angular velocity. It will be the derivative of angular position with respect to time. And the symbol that we're going to use for angular velocity is the Greek letter omega. And that's the lowercase omega. And so not a W, that's an omega. So omega is, by definition, the first derivative of angular position with respect to time. That's angular velocity. It will have dimensions. Even though theta does not have dimensions, time does. And so this might be measured in radians per second, or this is the same as seconds to the -1 power, because the seconds are in the denominator and the numerator has no dimension. So you'll see both of those discussed, radians per second or seconds to the -1. Similarly, angular acceleration will run the same way. Angular acceleration will use the Greek letter alpha, and angular acceleration will be defined as the derivative of angular velocity with respect to time, or the second derivative of angular position with respect to time. And I could write this out as omega dot or theta double dot. And again, this is going to have units, and those units are going to be radians per second, or radians per second squared, or just seconds to the -2. Those will all be equally used. They all mean the same thing. It's how fast is angular speed increasing or decreasing. Well, there is a direction, and we'll talk about direction later, but right now we're just going to consider how fast is changing. And in this case, how fast is how much angular speed is changing. Angular mass we're going to get into in detail in this lecture, but basically angular mass is what we call rotational inertia or moment of inertia. Rotational inertia or moment of inertia is a measure of how difficult it is an object to change its rotational speed. So think for a moment about a merry-go-round. If you've got a merry-go-round at a playground and there's several people on board the merry-go-round and you're trying to rotate it by pushing the merry-go-round, that's going to be very difficult to do. But if all those people jump off, then rotating the merry-go-round becomes a lot easier. Well, of course, all those people jumped off, so the merry-go-round has less mass, and that does have something to do with it. But we would also discover that if all of those people moved towards the center of the merry-go-round, it would be easier to rotate the merry-go-round. And so angular mass, unlike regular mass, not just a measure of its mass, and it's also a matter of where the mass is positioned. And we're going to find when we talk about rotational inertia, there's going to be a positional difference between an object's rotational inertia and another object. You can think also of an iron bar, and if I clamp some weights to the iron bar and you try to rotate it, it's going to be difficult when the weights are on the outside. But if I move those weights to the center, the bar, even though it has the exact same mass, will be much easier to rotate. The units we'll see then for angular mass or rotational inertia will be mass times length squared, or in the metric system, kilograms times meters squared. Angular force is going to be very much related to Newton's second law. Remember, regular force was equal to mass times acceleration. Well, angular force we're going to call torque, and we give it the Greek letter tau. So that's the symbol that we use for torque. And it is, in fact, a vector quantity, just as force is and acceleration. So tau will equal angular mass and angular acceleration. And again, we've already talked about that being alpha, and it is a vector quantity. There are going to be other methods of measuring torque, but fundamentally, this is Newton's second law. Force equals mass times acceleration. Angular force equals angular mass times angular acceleration. Well, recall angular momentum then must be very similar to linear momentum, which was equal to mass times velocity. And so angular momentum, and I'll use the letter L for angular momentum, is equal to angular mass times angular velocity. Again, also a vector quantity. We'll really dig into those vector quantities later on, not in this lecture, but in a later lecture. You can see that the units for angular force are going to be different. That's kilograms meters squared when it comes to the angular mass or rotational inertia. And then recall that angular acceleration was in seconds to the minus 2. So that's kilogram meters squared per second squared, which you may recall is the same as joules, but we will never use joules for torque. We're just going to leave it as Newton meters or as kilogram meters squared per second squared. Never joules. Joules is strictly energy. Angular momentum in a similar fashion would be kilogram meters squared per second, or times seconds to the minus 1, however you want to look at that. So angular momentum does not have the same units as momentum does. Now work, recall, was equal to force times distance. It was a scalar quantity, even though force and distance might have been vectors. Angular work is still going to be work, and it's going to equal force, which is an angular force, that's a torque, times a displacement. The displacement is theta, the position, or delta theta might be more appropriate. Now in this case, the units are actually going to work out nicely because the units for torque are kilogram meters squared per second squared. Right? So kilogram meters squared per second squared. The units for theta are radians, but those are dimensionless quantities, so when I multiply those together, I just get kilogram meters squared per second squared. And in fact, that is just going to be joules. Now, it is joules in this case because I'm not talking about a torque, I'm talking about a work. So all of these things we've talked about up until angular work, angular position, velocity, etc., they all have different units than their linear counterparts. But work, and we'll see here in a minute, and kinetic energy do not have different units. They are, in fact, the same units that we had back in the linear world. So work doesn't care about rotation or translation. Work is work. Same thing with kinetic energy. Now kinetic energy, you may recall, was 1/2 mv squared in the translational world or the linear world. Well, kinetic energy will be 1/2 mass, but now I'm talking about rotation, so that's I, times speed, but that's angular speed, so omega squared. And again, if we look at the units, I have kilogram meters squared when it comes to the I, and then omega is seconds to the minus 1, but that's squared, so seconds to the minus 2. And that is kilogram meters per second squared, which is a joule. So kinetic energy and work very much related again. The work and energy theorem will still work, is still valid, except that we're not going to have an integral of force times dx. We'll have an integral of torque times d theta. So all of these quantities are still going to work out for us. Well, back in the acceleration days, when I had a constant acceleration, we were able to write equations, kinematic equations for the distance something traveled or the speed at which something traveled. These same equations are going to hold if I have a constant angular acceleration. So let's recall a few of those equations. And I'll stick with one dimension for now. So x equals x naught, position equals original position, plus original velocity times time, plus 1/2 times the acceleration times t squared. You may also recall velocity was equal to initial velocity plus acceleration times time, or velocity squared equaled initial velocity squared plus twice the acceleration times the displacement delta x. Those were just some of the equations that we worked with back in some of the first chapters when we talked about standard kinematics, constant angular acceleration or constant acceleration back then. Well, now I have constant angular acceleration. The equations haven't changed, but we're going to change all the symbols to the angular symbols. So angular position equals initial angular position plus initial angular velocity times time. Time is the one thing that stays the same in the linear world and in the rotational world. And then plus 1/2 the angular acceleration, which is alpha, times t squared. Angular velocity equals the initial angular velocity plus the angular acceleration times t. Angular velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. All of these equations that we had back in the day of constant linear acceleration still exist for constant angular acceleration, but we have to change the symbols in order to correspond to the correct dimension or quantity that I'm interested in the rotational world. So let's look at some relationships between angular quantities and linear quantities. Start off by talking about an angular speed, I should say angular speed, of a point on a rotating object. So if I have some arbitrarily shaped rotating object, and here's an axis of rotation, and for the sake of argument we'll say it's going in the counterclockwise direction. All the points on the object will go around in a circle at the exact same speed, the exact same angular speed. That's going to be constant. So imagine again, if you're on a merry-go-round at, say, an amusement park and you sit on your horse and you go around in a circle, no matter where you are, everybody goes around the circle with the same angular speed. You all take the exact same amount of time to go one time around the circle. Now we already know the inside horses and the outside horses move at different linear speeds, but the angular speeds will always be the same. And as that object goes around in a circle, it goes through a certain distance, and that distance is going to be the circumference of the circle. And so the circumference is equal to 2 pi times the radius, which is the distance from the axis of rotation. So it's going to be different for different horses. As you move towards the outside, you're going to travel a farther distance, a farther circumference, because you have a larger radius. But we all go around in the exact same amount of time. So that amount of time is referred to as the period of rotation, and we use the letter t for the period. So this is the time it takes for one full revolution, right? The time for one full revolution. That's the period of the rotation. Conversely, there's the frequency of rotation, and this is the number of revolutions per unit time. So the number of revolutions per second in general. I'll just say per unit time, but in general that means per second. Well, it turns out the frequency, which I'll use the letter F for most often, is equal to 1 over the period. Okay, and if you think about it, the period is the time for one revolution, and the frequency is the number of revolutions per time. And so it makes sense that they are actually the inverses of each other. And then arc length, we want to keep in mind if I have an object here at some other radius r, and if I rotate through a portion of a circle, not the full circle, but some angle theta, then this length This red length here is an arc length, and that arc length S is equal to the radius times the angle theta. Now the angle theta must always be measured in radians, never in degrees. So the arc length S is equal to the distance from the axis of rotation times the angle measured in radians through which the object is rotated. And of course, if that's a full circle, 2 pi radians. So a full arc length of a circle is the circumference. So the tangential velocity, let's just think of an object on a circle. Tangential velocity of that object would be its linear speed. And if I'm a distance r from the axis of rotation, well, distance equals rate times time. So if the distance is the arc length, r theta, and it takes a certain amount of time to go through that r theta, so that would be divided by some time, this would be the tangential velocity. Well, if you think about it, theta over t is the angular velocity. So this is r times theta over t, but that's the angular velocity, and so that's r times omega. So the tangential velocity is equal to r omega. And we're going to assume that the radius stays constant. If you get into later courses, the radius will change in many cases. And then things get to be a little bit more difficult. But for now, just assume a constant radius. Omega might be changing, and in which case the tangential velocity is also undergoing some change. So there'd be a tangential acceleration in that scenario. But if the radius is constant, then the tangential velocity is going to be that radius times the angular velocity. Well, in a similar fashion, the tangential acceleration, which I'll call AT, is equal to the radius times the angular acceleration, pretty much in the same relationship that we had up here. So tangential acceleration equals radius times angular acceleration. Now the normal acceleration is what we've also called the centripetal acceleration. And so that is related to linear velocities. So the centripetal acceleration, which I'll call AN for normal, or we might call it AC for centripetal, that's equal to v squared over r. You might remember that when we talked about uniform circular motion. But v is the speed of the object, the tangential speed. And so this is actually equal to r omega, quantity squared, because that's the tangential speed, divided by r. So the centripetal acceleration might be written as r squared omega squared, all over r, which is the same as r omega squared. So v squared over r is legal, r omega squared is legal. They're the same thing. It just depends on what you're given as to which of those formulas you want to use to calculate out that normal acceleration.